Hi there, my name's Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in a previous video, I looked at common source amplifiers with diode-connected loads. I looked at the case where the main amplifying transistor was an NFET, and the load could either be an NFET or a PFET. I didn't look at the PFET case because I couldn't get that to simulate. It turns out the key to getting the PFET case to simulate is to put a small capacitance at the output. I have no idea why this is necessary in the PFET case, but not necessary in the NFET case, but there it is. Here I have my main PMOS transistor, and down here we see the diode connected load. And here I'm using a 10 femtofarad capacitor. In the demo I'm about to do, I found if I used 1 femtofarad, it wasn't enough, and the simulation would only work for lower input voltages. So in this particular demonstration, I'm setting the parameters for both transistors to be the same, and I'm using a kappa of 1 for both of them. So let's try simulating that and seeing what happens. We have a nice slope. It looks pretty much to be -1. Let's check that out. So for inputs between 1 and 2, we have outputs between 1.4 and 0.4. So that's kind of a nice -1 slope. And it's leveling out at these lower input voltage ranges. I should mention that I'm kind of assuming you've already have seen the other video I did on these common source amplifiers with diode connected loads. So I will put a link to that in the description, so you should go check that out if you haven't seen that already. Anyway, let's see what happens if I take the kappa for my diode connected load and set that to 0.5. Okay, so in this particular example, I do get a steeper slope. Let's try to find a nice linear region. Let's say we have inputs from 1.6 to 2.2 volts. That corresponds to a range of 0.6 volts. And the outputs that we get in that region look like they're around 1.5 to something like 0.3 volts. So that's something like 1.2 volts. Okay, so that would be like a slope of -2. Let's flip this around. So I'm going to set the kappa for the diode-connected transistor back to 1, and then I'm going to set my main amplifier transistor to have a kappa of 0.5. And if we check this out, we should get a slope of 1/2, or I should say a -1/2. And actually, it does not want to simulate, does it? Oh, so let's take this capacitor and boost it up a bit. How about let's try 50 femtofarads? Why does it do that? Anyway, let's try simulating that and see if it's happy with that bigger capacitor value. Ah, it is happier. And look at this. I have this really nice slope here. So the input ranges over 2.5 volts, and the output is going from 1.4 down to, let's take a closer look at that down here. Let's see, down to around 1.5, somewhere around those thereabouts. Oh, they continued a little bit further here to that point. Okay, so that basically corresponds to a slope of -1/2. And of course, we could play a bunch of other games of changing the different threshold values for the different transistors, or changing the threshold currents, yada, yada, yada. And at some point, I'll probably put all of these files on my GitHub so you could download them and play around with them yourself. For right now, what I really want to do is pull up the other example I have where we're using a PMOS transistor as the main amplifier transistor, but we're using now an NMOS transistor for the diode connected load. I don't know why it is, but this particular set of demos, it wants to have all this white space above and below it. I'm not sure why these files want to do that. It's not doing that with any of my others. It somehow got introduced at some point and I can't seem to get rid of it. Like if I copy this and try to go up here and move it up there, it puts it back here. I'm not sure what's going on. Anyway, here I now have a diode connected NMOS transistor acting as my active load. And in case you're wondering why the PMOS and the NMOS are different sizes, when I updated this software to work in Scilab 6 instead of Scilab 5, imported it over to my Mac and all that. For some reason, when I load in new transistors into an existing model from earlier versions, these come up with smaller rectangles. I don't know why, but it seems to simulate fine, so whatever. Okay, same game, slightly different circuit. I'm going to start with both of these transistors with a kappa of 1. Let's simulate that and see what happens. Okay, that pretty much looks like what I got before in the case where both transistors were PMOS and both kappas were the same. Okay, now let's play a game where I take this NMOS transistor, that's my diode connected load, and set kappa for it to 0.5. That pretty much looks like what we had previously for a similar configuration of kappas. Okay, let's finish the test sequence here. Let's change the main amplifying transistor to 0.5, and let's change the diode connected transistor to have a kappa of 1. And if we simulate that, let's see if we get something that looks like what we had previously. And it turns out that we do. So that's very interesting. It doesn't look like it very much matters whether we use a PMOS or an NMOS transistor for our diode connected load. This contrasts with a phenomena I discovered at the end of my previous video, and if anyone has any insight into what's going on here, please leave a comment below.